Everybody, I'm going to do this short video to make hard to understand concept of VSEPR simple. So even before we go to valence shell electron pair repulsion theory, nicknamed lovingly as VSEPR by the chemist, let's study why even know about this theory. Why is it even important? Well, have you ever wondered how do we smell? Or how come our dogs have a better sense of smell than humans? Well, those answers may actually lie in the study of VSEPR theory. So let's look at what VSEPR theory is and how does it tell us about our sense of smell. Well, VSEPR or valence shell electron pair repulsion theory is a very simple theory which helps transform the 2D molecules written with Lewis structures into a 3D shape. Because as we all know, in real life, molecules exist in three-dimensional shapes. So if you know the Lewis structure of a molecule, knowing VSEPR theory, you can actually predict its 3D geometry in real life. For example, if you knew that water molecules structure is like this, where there are two lone pairs on oxygen, which is the central atom, and each hydrogen is bonded to the central atom by single bond, knowing this and applying the concept of VSEPR to it, you can predict that this is actually a tetrahedral molecule. So how do we go from these flat two-dimensional drawings to these 3D molecular shape using VSEPR? VSEPR theory has three main points, and it is rooted in the simple scientific phenomenon that like charges repel each other. Like charges repel each other, and you know that. So in the 3D space, as atoms combine to form molecules, if this is the central atom and there are two other atoms that combine to form the molecule, these side atoms tend to be as far from each other and the central atom as possible without breaking the bond. So the farthest these two side atoms, which I'm going to call A and B, are going to be from each other is by 180 degrees. Because each of them are still bonded to the central atom, they can only move this far. And because when they move the farthest, they minimize repulsion, or they are most quote unquote stable or are in a lowest energy state, this is the structure of the molecule, and we call this structure as linear. Now imagine if around the central atom we have three other atoms bonded to it. Now in this, these atoms will tend to be farthest from each other to minimize repulsion, and that farthest will give them the shape of trigonal planar. And in this, they are all in the same plane. And the bond angle here is 120 degrees. Now, I would like to clarify a term before we go any farther. That term is electron domain. Electron domain in VSEPR refers to either atoms bonded to central atom, because the atoms have electron cloud which have electrons, and because each atom's electron cloud has these negatively charged electrons, they tend to be far from each other. Or electron domain could be used for bonded pair of electrons, the shared pairs between different atoms. Or electron domains could also be the lone pair of electrons on the central atom. When we talk about lone pairs of electrons, we only refer to the lone pairs present on the central atom in VSEPR theory and not on the side atom. And guys, VSEPR theory only applies when you have a central atom and other side atoms attached to it. And we have a shortcut to represent these molecules. We call them ABE or ABX type of molecules, where A represents central atom, B is the bonded, and E are the lone pairs. As you can see in this structure, there's one central atom, two bonded, no lone pairs on the central atom that we can see here. So it will be AB2 molecule. So all molecules that have AB2 structure per VSEPR will have a linear molecular and electron domain geometry or linear shape. Any AB3 molecules will have a trigonal planar shape. Now what happens when you have 4 electron domains around the central atom? Something interesting. Once you have 4 electron domains, the farthest they can be from each other in single plane is only 90 degrees, because 90 times 4 is 360. However, if they are not in the same plane, then they can increase their bond angle to be 109.5. And this shape is called as tetrahedral shape. And in this shape, 2 of the bonds are in the plane of the screen. One is jutting out and one is behind the screen. And this shape is called tetrahedral. It is kind of hard to visualize a 3D shape on a 2D medium. So I'm going to now take you to an animation. And in this animation, you can now see how the 3D geometry is impacted. So this one is, let me remove this. Okay, let's add 2. And no matter how close you try and bring them, you'll see when you let the mouse go, they will always be at 180 degrees from each other. And if we select the bond angles here, it will also show the bond angles. You can rotate the molecule, and it's a pretty nifty interactive. Let's add one more. And now you can see the bond angle becomes 120 degrees. Notice that all 3 bonds are in the same plane. Let's add one more, and with that you can clearly see now they are not in one plane. This one behind is behind the screen. This one is jutting off, and these 2 bonds are in the plane of the screen. So by going or spreading out in the 3D region, these 4 bonds around the central atom have increased the bond angle or minimized repulsion between them, which gave this molecule a tetrahedral shape. Then you can keep attaching. You can attach one more, it becomes trigonal bipyramidal. And if you attach one more, that becomes an octahedral shape with all 90-degree bond angles. And you can play around with this animation. This is from FET Colorado. But right now, I just wanted to bring your attention to the basics of VSEPR. And let's go back to our talking screen. So we were talking about the shape of the molecules because VSEPR states that electron domains tend to minimize repulsion, and due to this minimization of repulsion, the electron domains move farthest from each other, which renders these molecules a special shape. Now, another very important point of this theory is that 2 lone pair repel each other more than a lone and a bond pair, which repel more than 2 bond pairs. And now let's look at why is it so. So if you think of the lone pairs, remember in VSEPR when we talk about lone pairs, we are only concerned about lone pairs on the central atom, not on the side atom, on the central atom. And with the example of water molecules, let's examine why do lone pairs have more repulsion than a lone and a bond pair. Let's say this is the electron cloud of hydrogen, where that lonely hydrogen's valence electron is moving about. And let's say this is the electron cloud of oxygen, where oxygen's valence electrons are moving. And along this internuclear axis is their shared pair of electrons. one coming from hydrogen, one coming from oxygen. So they have all this internuclear space to be far from each other. Similarly, between this hydrogen and oxygen, they have all that internuclear space to be far from each other. However, if we are talking about lone pairs, these lone pairs are present in the electron cloud of oxygen atom, which is not a huge space. So they are closer to each other. And because of this closeness, the repulsion between two lone pairs is greater. And what happens when the repulsion is greater between these two lone pairs? They tend to push these bond pairs a little bit closer together. As a result, the bond angle between the hydrogen, oxygen, and hydrogen, this bond angle, instead of being 109.5 as it should be in a tetrahedral electron domain geometry, it ends up being 105 degrees or 104.5 degrees, a significant decrease due to the increased repulsion from lone to bond pairs. And this again impacts how the geometries are changed. Now, we just seen that we had AB2, AB3, AB4, AB5, and AB6 molecules. Now, if we start replacing the bonded pairs with lone pairs, due to the increased repulsion of lone pairs, the bond pair will keep decreasing. So this bond angle, instead of being 120 degrees with a lone pair here, will be less than 120 degrees, which in turn impacts their geometry. And there is a lot more to it, but I think I'll stop here. And I'm sure before I go, you'd want to know, so what does it have to do with the smell? Well, the smell, the way we humans or dogs smell things is we have these little scent receptors in our nose. And these scent receptors is where the fragrant molecules get attached. So when you smell something, the molecules actually leave that substance and come and attach to your scent receptor. And a certain molecule can only attach to a certain scent receptor because of the special 3D structure of that molecule. And this special 3D structure is dictated by VSEPR geometry. And when this molecule attaches to the receptor, it sends a signal to our brain for that particular smell. And that is how we smell. Now, to the question, why do dogs have better sense of smell than human beings? The answer is dogs have about 220 million scent receptors in their little noses, while we humans have measly 5 million scent receptors. So our sense of smell is not as keen as our dogs. And that is all for today. Thank you for listening. If you have any questions, email me, contact me. I'll be happy to answer. Thank you again.